So my name is Darren Hart, and I work with Intel's Open Source Technology Center. And you guys may know me from my time on working with the real-time Linux kernel as a maintainer of the platform drivers x86 tree, Yocto project, Minnoboard, and now primarily safety-critical Linux, which is a bit of a full circle for me with its dependency on real-time. That's going to be interesting. Thank you. Okay. Well, Linux was incapable of seeing the display, and my document is not working in my backup system, so I will try a PDF, which I exported just in case, which looks like we will need. Backup version number 3. Okay. If anyone knows the hotkey for slideshow, let me know. Yeah, that wasn't it. Okay. So now we're talking about functional safety. To give us some background, about 150 years ago this year, there was an independent group of engineers in Germany that started inspecting steam engines and boilers. This was a DU umlaut V, and I won't try to pronounce it since I have Germans in the front row. So by 1871, they were so successful that they had begun to replace government inspections, and they started to expand the scope of their work. Over time, geographically, there were 43 of these TÜVs, now with a T because they had expanded their scope to include additional industries beyond boilers and steam engines. So these were accredited groups of expert engineers that would provide independent assessment of standards compliance. So today, they work in multiple industries: nuclear, aerospace, industrial process and control, and more recently, automotive. But let's talk about a modern example that deals with functional safety. So this is an A400M, and one of these crashed in Spain last year when 3 of its 4 engines failed to respond to pilot input. These are heavily automated systems where each of the 4 engines has an electronic control unit which interprets the engine sensor data through a set of torque calibration parameters and then translates that into the optimum mode for the engine to respond to what the pilot asked it to do. These files had been accidentally deleted during a software installation. What that ended up doing was it made the sensor data illegible, incomprehensible to the ECU, and the ECU reverted to a safe state, which was idle mode, because if an engine had kind of run away and gone crazy, they didn't want these engines to just come back up to full throttle. Unfortunately, nobody considered the fact that 3 of these might enter that state at the same time. So ultimately, we had a situation in which software didn't fail. Matter of fact, in the vernacular of functional safety, software does not fail. Software is modified, and in this case, software had been installed, but the process had failed. So this really illustrates a very central point that I want to make today. Functional safety requires that everyone involved, from the design, the specification, the conceptualization, the operation, the maintenance, even down to disposal and decommissioning, needs to be working with a system view. And I mean system in the very highest sense of the word. So this includes all of those things which we just mentioned. We're going to do a safety integrity level analysis of laptops connected to these things, because somebody's going to die. Okay. So we need to fight our natural tendency to focus very specifically on what we understand. It's very easy when we work on our product, on our function, on our code base, to focus on that bit. But everything that we do when we're working on a safety critical system impacts the system as a whole. Okay, so standards. Standards provide a language and a framework for us to manage complexity. Just like each of the countries represented here by these flags sort of defines, maybe not a language, but many languages, infrastructure, laws that people work together and within. Standards also help facilitate communication, and they encapsulate domain specifics, which then in turn helps us to scale. We'll talk a little bit about what that means. Functional safety refers to the probability of a system operating correctly in response to its inputs and various hazards, whether they be operator error, environmental controls, or random hardware faults. So again, functional safety is the probability of a system operating correctly with respect and in response to its inputs. It is ultimately, though, about defining an acceptable level of risk. And it's specific, today anyway, we are specifically talking about electrical, electronic, and programmable electronic systems. Those terms are important, and they should give you an idea of the types of systems that the specifications we're talking about were written for. I did not say computer systems, for example. Now, I've used the word risk a few times. Throughout these standards, you'll find terms like risks, hazards, errors, and failures, and they all have specific meanings for that stage of that process in that standard. And unfortunately, they do differ a little bit across standards. So we're going to use them a little bit loosely today. But risk, I think, is important to define. Risk is the product of probability of failure and severity of failure. Product of severity and probability. So a very low, unlikely event that isn't going to hurt anybody is very low risk. Really low probability with a very high severity, lots of people are going to die, is a medium level risk because it's very unlikely to happen. Connect the dots from there, I think. Okay, so the top-level sort of basis standard for functional safety, IEC 61508, forms the basis for a number of domain-specific standards which encapsulate domain-specific. So automotive, for example, has a number of specific properties that apply to every vehicle made, every passenger vehicle under 3.5 tons that operates on our roads can be considered under the 26262 standard. Okay. Safety integrity levels are a very key aspect of functional safety. 61508 defines 4 safety integrity levels. There is indeed one down there. SIL levels 1, 2, 3, and 4. And each of these has something to say about the processes that are used and the methods that are used in the development of a safety critical system. So for example, fit ratings or failure in time really is a frequency in how often something fails as measured in billions of hours. It ranges somewhere between 10 to the -1 to 10 to the -9. SIL 4 allows for 1 failure, or what is that exact wording? Let me get that right. Language is important. SIL 4 allows for 1 occurrence of a dangerous failure of a safety function in 1 billion hours of a high-demand operation. Basically what that means is if your specification requires SIL 4, try again. Don't do it. That's the no-go zone, is safety integrity level 4. And you'll see that as it's translated across domain-specific specifications where The rail system, for example, specifies safety integrity levels 1 through 4, but they map to its parent, I use loosely, to its parent specification, SIL levels 1, 2, and 3. There is nothing up here in the red zone that's similar to 61508's SIL level 4 in rail. The same is true for auto. ASIL D being its most rigorous for certification, safety integrity level is more or less equivalent to the high end of the range of SIL 3 in 61508. So each of these safety integrity levels define some of these methods that we can use. 61508 used language like formal methods. Formal methods are required in software analyses for 61508 at SIL level 4, which is another reason to stay away, because as we move closer to using very complex hardware and very complex software systems, formal methods as applied to 20, 15, 25, however you want to measure it, the tools and I couldn't agree, million lines of code within the Linux kernel, this is just a non-starter. SIL level 4, not going to happen. So SIL 3 does require some amount of semi-formal methods. There's talk of using automated tooling to enforce consistency and reduce maintenance tasks, as well as errors introduced in that. Traceability is an important aspect of safety integrity levels. And traceability is when we're talking about software safety requirements as being traced to safety requirements and the perceived safety needs, as well as every software element or any element within a system needs to also be traced back to the safety requirement that required it. And one of the reasons this is a good thing is you don't end up with any faults due to a software component that you didn't actually need, because it won't be there, because it can't be traced back to the safety requirement. Therefore, you don't include it in your product. This helps minimize your space, or in security terms, your attack surface. In fact, SIL 4 is actually explicitly discouraged within 61508. Okay, I think we've covered all of that. So let's put this in a little bit more concrete terms. So this is what we can call the automotive safety integrity level assessment grid. And the way this works is there are 3 criteria. You have severity, we'll call S, exposure we call E, and controllability that we call C. And each of these increases in its range. So severity is how severe are the injuries? Is someone going to get some minor cuts and scrapes? Is someone going to get broken bones, internal injuries? People likely to die. That's 1 through 3. Exposure is how likely is the hazard to occur, from not at all likely to very likely. And then controllability is how likely is the operator able to control the hazard should it occur. And in this case, 0 is totally under their control, and 4 is no way. They can't deal with it. So the way this works, and again, down there in the bottom, D, ASIL D is the red spot on the black curtain down there. And as you go up, each time that you reduce one of the criteria by 1 factor from its highest level, the ASIL rating also decreases accordingly. Once you get to a point where either at their minimum level or high enough up in the stack, you enter what we call quality management, or QM. QM effectively has low enough risk that there is assumed to be no safety requirements associated with that element. So let's talk about a few examples. So let's talk about a in-vehicle infotainment system and review it according to this. So let's say there was the power supply unit had a random hardware fault and it cut power to your IVI system. What is the severity of that failure? Anyone want to throw out a number? 1? Okay. One's reasonable. I would almost argue 0 because nobody's died by not listening to their music for 5 minutes. Those of you with kids might disagree. What is the exposure? How likely is this to happen? Hopefully the power supplies in these things are pretty decent, but it could happen. I'd argue 1. And then controllability. How likely are you to be able to safely, maybe not enjoy it, but how safely are you able to navigate the vehicle without your infotainment system? I would expect that to be very well, which is a 0 here, 0 or a 1. So this comes well under the quality management ASIL rating. So let's take another serious example then. What about an emergency braking system? Let's say it uses cameras and your car is dirty. I know we use radar and we use sonar, but humor me a little bit. Let's simplify the example. How likely, exposure, how likely is your car to be dirty? Mine's really dirty, so I'm going to say it's pretty high. Now, the severity of such a system, what would you suggest that is? In the event, the hazard is that your car is dirty and the camera doesn't work, so the emergency braking system can't work. What is the severity level of that? Well, let's say it's not supposed to be dirty. What's the failure? The failure means that it's an emergency braking system, so the car fails to detect something that's coming up. The brakes do not engage. It's not braking when it should. Correct. Yep. So 3, I'd agree. People might die, it's 3. But what is the controllability of the driver if the emergency braking system stops working? Pretty high, right? Yeah, it's an emergency system. It's augmenting the driver's capability. So the emergency system, that brings us up a few levels in here, and my assessment was I'd call this an ASIL B. In practice, because of the argumentation that this is a augmenting system, the driver does not depend on this at all. In practice, these are often ASIL A or even QM. However, if the braking system engaged when it shouldn't, it's a very different failure and very much justifies an ASIL B rating. Okay, do I give this last example? I think we'll skip the last example in the interest of time. So these are all hypothetical examples, but they are indicative of the type of logic that we need to start thinking about from the larger system perspective. How do we determine the safety integrity level of the elements of our system? So this is the type of logic that's applied. In fact, 30% of the faults that we experience in industry are due to an inadequate safety integrity level specification. So this is a very significant part right here. Okay, so functional safety is inherently an end-to-end. Please don't use this as like formal documentation. I threw this together from some slides, and I'm not going to talk about every single point. But what I wanted to get across was safety is considered throughout this entire life cycle, all the way from concept to safety requirements to your validation planning, installation and commissioning, updates to the systems, repairs in the field, decommissioning. This whole process here is involved. And each one of these then gets deeper and has its own process associated with it as well. But a constant throughout accident reports is the failure to sustain a system view somewhere along this path. The context in which you're talking about a system is absolutely critical. So let's talk about a frivolous example. Let's consider a robotic vacuum cleaner. Now, we'll talk about it under 26262 for automotive. It is a vehicle. It is under 3.5 tons. It doesn't technically have passengers, I guess, but rather than define a new model, let's go ahead and use ASIL. So I'll throw out some ideas for you. So it's battery powered. It wakes up and starts to begin cleaning on some programmed schedule that you devised, and it has to return to its dock to charge. So let's define context. What is the context of our robotic vacuum cleaner? Where does it operate? Can we have some assumptions? Home, okay. Business, okay. What time does it operate? Does that matter? At night, during the day? When you're at work? Okay, good. We could go on about context, but that gives us an idea. What kind of a safety integrity level would you assume that a robotic vacuum cleaner has in car terms, in automotive terms? ASIL A, ASIL B, C, is it D, is it QM? QM? Okay. Now let's expand the context a little bit. Let's say that the operator has a dog and the dog chews on it if he leaves it on the floor. So before he left to work, he took the vacuum cleaner and he set it on the counter. And it woke up and it started to clean the counter. And then it drove over to the cooktop. And the cooktop was touchscreen. So it turned it on. And then it drove around in circles and melted itself into a little stinky puddle on the top of the cooktop, with leaving a horrendous stench and 100,000 euro in damage to the premises. So would that change your assessment of its safety integrity level? I don't know if it has, actually, but this happened. Right, outside of the recommended use case, sure. But context is critical because people will do things that you don't expect. We cannot account for every single element within the context for a device. Okay. Now let's discuss context of a more serious example. In 1996, an A320-211 flying from Frankfurt to Warsaw attempted a landing in heavy rain with 6 millimeters of water on the runway with a strong tailwind, which caused the crew, according to the manual, to increase their flight speed. The A320 has 3 braking systems. It's got reverse thrusters. That's when either the engines open up like this or the flaps come way down and it takes the thrust from the engines and it pushes it forward. Okay. It's got air brakes, so the wings give it a lot of lift and open up like this and put a lot of air resistance. And then it's got wheel brakes, just slows down the wheels. Each one of these has criteria that must be met before they will be allowed to engage. So for the reverse thrusters, both struts must compress to 12 tons. For the ground spoilers, both struts must be compressed or the wheels must be turning at an equivalent of 72 knots. The wheels themselves, in order for the brakes to engage, must be rotating at least 80% of the velocity as reported by the aircraft's computer. Now, when the plane touched down, only one of its struts compressed to 12 tons. So that prevented the reverse thrusters from coming on. In turn, the rain-slick runway prevented the wheels from rotating. It was hydroplaning. So because neither criteria were met, the ground spoilers didn't come on. Also because the wheels were hydroplaning, the wheel brakes didn't work. So it was a full 9 seconds before the second strut was fully compressed sufficiently in order to allow for the reverse thrusters to engage and for the ground spoilers to come on. 4 seconds after that, the wheels started spinning, which allowed the wheel brakes to come on. By the time all of the braking systems were engaged, there was insufficient runway to stop, and there was insufficient runway to take off. So in this event, 2 people were killed, and 50 people were seriously injured. This accident was deemed pilot error because they failed to follow various processes throughout this circus of errors, which lasted 15 seconds. Communicating all of that to the pilots is a very difficult task. If we were to abstract this, I'd call this a failure to communicate in a number of ways. The accident report, however, did make recommendations that an emergency override be in place so that pilots could actually force the reverse thrusters to come on. And some of those were implemented. Now, another unsubstantiated report that I haven't been able to verify was that they also reduced the weight from 12 tons to 2 and eliminated the wheel spin. I think this speaks highly about a system view, and it speaks strongly towards context as being critical. Did they have domain expertise? Would a pilot have approved those criteria for those braking systems? Domain expertise is very critical in defining safety specifications. There's one other point I wanted to make about that. What was it? I don't recall. Now, it is generally considered and accepted that it is impossible to comprehend all possible faults in a system. Complex systems like the A320, for example, may not fail with a common cause. They may not be able to isolate the specific hazard responsible. So standards based on hardware failure do not adequately address complex hardware and software systems. Rather than try to summarize, I'm going to read a quote from one of NASA's accident reports. This methodology showed that it was very important to examine not only single low probability and high consequence mishap events, but also high consequence scenarios that can emerge as a result of the occurrence of multiple high probability and low consequence or nearly benign events. Contrary to common perception, the latter in its aggregate is oftentimes more detrimental to safety than the former. So a collection of simultaneous, high probability, low severity events created a situation that could not identify a common cause. Why did the A320 crash? It's pretty hard to say because of X. Right? There were a sequence of hazards that all occurred at the same time, which presented a nearly impossible situation to the crew. To move the state-of-the-art forward, these systems that we're building demand more computational power, that demands more complex software, and that software is not going to be written from scratch, and it is not going to be written in a form that is compliant to IEC 61508, which was largely written for microcontrollers. So we have traditional methods of reducing the safety integrity levels. We can run redundant, diverse systems parallel that run the same software stack. But we can do better than that. We can, instead of fighting complexity, I think we can find ways to leverage complexity. So there are many ways that we can do this. Our modern CPUs today are so complex that they are inherently random in a number of ways. For example, you'll never find, over here, I got Linus in the front row here as I'm waiting for him to, but never find the state of a system as represented by its cache to be identical in any two systems. Even if you start them at the same time, running the exact same software, it's never going to be in the exact same state across those systems. There's one bit of inherent diversity. We've also got, I'm sorry, I've kind of lost my place a little bit. We have runtime variance. Two systems from user space, system call paths are nearly random from their perspective. There's so much other things going on that is independent of the application that it's running. The exact path that the system call will take through the system is really unknown by user space, which in turn provides a certain amount of diversity at the level of the application. So, but with this and various other mechanisms such as function multi-versioning, in which you can have multiple versions of a function that has different ISAs, compiled with different ISAs, which is normally used to enhance performance for modern CPUs without multiple binaries, can in turn be repurposed to run different versions of a function across different CPUs, for example. So we can leverage the inherent complexity of our modern systems in order to provide the diversity which we can then use to reduce our safety integrity level of a system or to mitigate hazards. Complexity is in fact something that we as a community in open source have, I think, embraced. I think it's the norm for us. The TÜV Rheinland has stated that they are very pleased to see a move towards open source, largely because change has been guided by accidents and deaths. And with open source, we have the opportunity to apply all the things that we all do every day, inspecting code, finding errors, getting it out there before it causes a problem. We are building a culture that encourages competitive competition. Fixing bugs is encouraged, not punished. We have a culture that encourages uncovering issues and not covering them up. There are no black boxes. Bugs can be found, bugs can be fixed. And very importantly, it's very difficult to compete with the breadth of deployment of the Linux kernel. Diversity of deployment across architectures, across number of cores, et cetera, provides a very strong case for code coverage. Safety culture in general. While I've talked a lot about hazard mitigation, the first step towards developing a safety system is hazard elimination. So how do you get rid of a hazard? If you can eliminate the hazard, it doesn't play into your integrity level. I'd love to give you a good example on that, but I think we'll run out of time. Risk awareness at all levels of our design. We can't just focus on the thing that we know, but we instead have to back up and consider the entire system. Safe design at all levels, and very importantly, in order for this to be successful, we have to be able to learn from failure, and we have to be able to do that without blame, because otherwise we won't do it. So with this in mind, the Open Source Automation Development Labs has, in conjunction with a number of member companies, has formed a project called SIL to Linux MP. If you attended FOSDEM, you may have heard of this from Nicholas McGuire, who presented an excellent presentation that was focused entirely on this. And if you'd like to learn more about this, that would be a really good place to start. I will put these slides up for the Linux Foundation. I'm not sure how much use there'll be, but there are links on it. So you can click on the link and go to the homepage for the project as well. Now, SIL to Linux MP aims at demonstrating the suitability of a Linux-based system for safety integrity level 2 or ASIL B, maybe C projects. The basic elements that it includes are a Linux kernel with the preempt RT patch and the PALC patches applied, glibc and BusyBox as its core runtime environment. And it works in this, where each of these elements of this code base are traceable back to the safety requirements for a generic system. It provides direction towards selection and architecture. It is intended to be run on 4-core systems, ARM or x86-64, and based, providing a POSIX SIL2 container as well as a Linux as well as a SIL0 Linux container, and with a monitoring system running on CPU 0. Now I feel like I say this a lot. SIL to Linux MP is not a Linux distribution. SIL to Linux MP builds a Linux distribution for you. What I mean by that is really the binaries are not what we're talking about with the SIL to Linux MP project. That is not the end goal. What SIL to Linux MP provides is a mapping interpretation of 61508 onto open source software. There's a lot of details we can go into, but dang it, I got to stop putting the important stuff on the bottom. This is a V chart that many of you that deal with more formal more formal development processes may be familiar with. Typically, what this will end with is the development, the actual authoring of the code. And one example here of what the project does is it attempts to map what would normally be development of code here at the bottom to what we do with existing software. So in order to use Linux, we're not going to go rewrite it in a compliant route. Even if we did, we couldn't use a number of the requirements in order to accomplish that. But what we can do is instead of the development process, we can change that to a selection process. And if it's a selection process, then rather than writing code at the bottom, we are configuring it, we are testing it, we are integrating it. And so we translate the language in the specification where we are non-compliant, and we present evidence for how we can be considered compliant. And then we take that, we lump it all together into a data package, and we have the TÜV review it. And we've done this. We're about halfway through the project with Silta Linux MP, and the TÜV is part of this project. They provide us with periodic reviews to let us know what they think of our progress. Like, hey guys, you're a year in, you spent this much money, you got no chance, just stop now. Right? That's not what happened. So TÜV Rheinland was there with us in Heidelberg in March, and they provided a review, and for every component that we presented to them, they responded with feasible or incomplete, which is exactly what you'd want from a project that is partway through to completion. So the project continues. It is on a good trajectory with strong support from TÜV. I believe that the TÜV is excited to see open source being leveraged for safety critical systems for all those reasons that we talked about and the safety culture that it builds. So I'm going to leave a little bit of time for questions. Really wanted to share this story with you about the REN5, but we can talk about it afterward if you have questions about it. So with that, thank you. Enjoy the conference. Travel safe. Any questions? Yes, sir.
Actually, sorry, a quick announcement. We added a medical devices or Linux and medical devices virtual better session talking about safety critical. That's tonight at 6:10.
Okay. So medical devices I had on here originally, and I actually took it off, partly because there is no specification for the device itself. We have specifications for the software development process, but there is no specification for the device. So that I'm interested to hear. This is tonight at 6:10? Okay. Yes?
How does the 61508 and its variance in application deal with the
I'm sorry.
How does the IEC 65108 map to DO 178B?
DO17, okay, so you're referring to the aerospace standards. 61508 is what's called a risk-based specification. The aerospace standards don't take the same approach towards certification, and I confess that is to the extent to which I have delved down the aerospace side. So maybe somebody else can answer a bit more about how the aerospace standards are, how they derive their safety integrity levels. But it is not risk-based as we've discussed today. And that's the best I can do for that answer. Yes, sir.
Are there any SIL models for like power systems and networks and things which?
Yes. What I'd actually recommend that you do, and I hate to say this out loud in this room, but if you go to Wikipedia and go to functional safety, you will find an excellent list of, hey, here's 61508, and here's all the domain-specific standards. Process and control is one of those. I don't know if that'll cover what you're interested in, but there are others as well. Yes?
How do you get into this situation, the probability or the impact of systems being hacked?
One more time.
How do you get into this, you've been talking about how likely something could happen or operate or into
Yes.
the impact. How do you get into the picture the fact that systems can be tampered with, like cars and planes being hacked?
Okay, tampered with. So I'm going to provide two half answers, and maybe that's Does that equal a whole? On the one hand, the exposure that we talked about for ASIL is highly subjective, and for that reason, a number of researchers are arguing to have it removed from the ISO 26262 standard as an amendment, partly because it's so subjective. On the other hand, you're basically talking about security, and I wanted to have some content in here to talk about how security maps to safety. Pretty much safety kind of becomes a superset of security, because anything that you can describe as an attack surface in security terms is a hazard for safety. But safety also has to include all the things like your bearings wore down and you got hit by a rock. And so safety has a much larger set of hazards to consume. So anything that you would identify as a security concern, I would also consider to be a safety hazard. Anyone else? Okay. Well, we'll finish a couple of minutes early. Well, I guess, we'll finish a couple of minutes early. Actually, if we have 5 minutes, I'll tell you this story. So this is the REN5. I can't pronounce it. Who's from Europe? Who knows how to pronounce the REN5 heavy lifter?
Everybody does it differently.
Excellent. So the REN5 heavy lifter is the 5th generation of the European heavy lifter. It's a rocket, right? Put stuff into space. The previous models had used multiple engines, and those engines had associated with them in the liftoff and the trajectory and the guidance systems, they had accelerometers. These accelerometers had vibration specs, and they would operate within a certain specification. With REN5, and throughout this process, they reused components from the previous, and they reused the accelerometers, but they replaced the engines with an engine, big engine. And the big engine had a lot more vibration. It also wasn't able to counter because it had 4. It didn't average them out. Ultimately, what happened on its maiden voyage was the accelerometers quickly went out of spec. The guidance system was blind, and it immediately entered into its self-destruct phase. So greatest fireworks in the world, I don't know, $20 billion set of fireworks. But this can be attributed to this is what we call a common cause fault. This one we can attribute back to a single point of failure, which was the accelerometers were out of spec in conjunction with the whole system, which then used a much larger propulsion engine. Okay. Well, with that, I'll let everybody go a few minutes early. Thank you for attending. Thank you for your questions.